Hi everyone. In the last class we have discussed about the spectrum of an operator with different examples. Earlier we discussed about how to divide the spectrum into different parts and how to get the spectrum using those parts. Today we will be discussing another way of dividing the spectrum into two different parts, and that will be useful for computing the spectrum. Okay, let us start with a bounded operator. So then we know that T has bounded inverse if and only if T is bijective. That means T is 1 to 1 and onto. Now this is by the inverse mapping theorem. Now this can be written as null space of T is 0 and range of T is full space H, and again this can be written as null space of T is 0, and the second condition we can write as range of T is closed and range of T is also dense in H. Okay, so if you combine the first two conditions, that is T is 1 1 and range of T is closed, we can say that T is bounded below and range of T is dense in H. So we can say that T has no bounded inverse, as T is not invertible in B of H if and only if either T is not bounded below or we can say that range of T is not dense in H. The second condition is again equivalent to say that range of T is closure is null space of T star perp. So null space of T star perp is not equal to H means, so this is null space of T star perp is not equal to H. That means null space of T star is not equal to 0. So we can again conclude that either T is not bounded below or we can say that null space of T star is not equal to 0. That means T star is not 1 to 1. Okay, so this is. Now let us take a lambda in C. Then the same condition we can apply, that T minus lambda is not invertible if and only if either T minus lambda is not bounded below or range of T minus lambda is not dense. Then T minus lambda is not invertible if and only either T minus lambda I is not bounded below or range of T minus lambda I is not dense in H, or this is if and only if null space of T star minus lambda bar I is not equal to 0. Now based on these two conditions, we can decide whether lambda is in the spectrum or not. We can say that lambda is not in the spectrum of T if and only if either T minus lambda is not bounded below or range of T minus lambda is not dense in H. Now with these two conditions, we can define two kinds of spectrum. The first one is the approximate point spectrum. It is denoted by sigma A of T as set of all lambda in C such that T minus lambda I is not bounded below. Okay. And the second one is the compression spectrum of T. It is denoted by sigma suffix comp of T set of all lambda in C such that range of T minus lambda is not equal to H. And we have shown that this is nothing but set of all lambda such that null space of T star minus lambda bar I is not equal to 0. That means lambda bar is in the point spectrum of T star. So this is set of all lambda in C such that lambda bar in the point spectrum of T star. So we can say that it is exactly the point spectrum of T star bar. So here denotes the conjugation, not the closure. Okay. That means we can write the spectrum as approximate point spectrum of T union compression spectrum of T. In fact, in this case, this need not be disjoint, but in the earlier subdivision of the spectrum, we have observed that spectrum of T can be written as disjoint in a point spectrum, the residual spectrum, and the compression spectrum. But this need not be the disjoint union. There might be common points for approximate point spectrum as well as compression spectrum. Okay, so let us look at approximate point spectrum in detail. So let us take lambda in the approximate point spectrum of T. Then we know that T minus lambda I is not bounded below. So let us quickly recall. If we have a bounded operator on H is bounded below if and only if there exists some K such that norm of Ax is bigger than K times norm X for every X in H. Now when we say that T minus lambda is not bounded below, means so T minus lambda I is not bounded below if and only for every natural number n there exists some element xn in H. In fact, we can normalize it such that norm of T minus lambda I acting on xn, this is less than or equal to 1 by n for every n. So that means we get a sequence of unit vectors so that T minus lambda I acting on xn goes to 0. This goes to 0. Yes. So this is equivalent condition for lambda in the approximate point spectrum of T. Now this is the first observation about approximate point spectrum, and the second one is the following, that we can easily show that point spectrum of T is always subset of approximate point spectrum of T, because if lambda in the point spectrum of lambda is in the point spectrum of T, then there exists x in H with norm x equal to 1 we can take, because x is non-zero, you can normalize it such that Tx is lambda x. Now define xn as x for every n in n. So then we can say that T minus lambda I xn is 0 for every n. This implies lambda is in the approximate point spectrum of T. Okay, so that means point spectrum is always subset of approximate point spectrum of T, and we know that the point spectrum need not be closed. So remark need not be closed. We have seen the diagonal operator on L2 with diagonal entries as lambda 1, lambda 2, lambda 3, so on. The point spectrum is exactly the sequence lambda n is in natural number, and that if lambda n converges to lambda, that need not be lambda need not be inside lambda need not be an eigenvalue. For example, we have looked at the diagonal operator with diagonal entries 1, 1 by 2, 1 by 3, so on L2. We know that T of En equal to 1 by n En, but 0 is not in the point spectrum of the operator. So the conclusion is that the point spectrum need not be closed, but we can always check that. We can easily verify that the approximate point spectrum is closed. It's a closed subset of the spectrum. In fact, it is compact because spectrum is always compact. So from that we can say that it's a compact subset of C. Okay, so this is about approximate point spectrum. Let us look at the compression spectrum. So we have seen that lambda is in the compression spectrum if and only if lambda is in the conjugation of point spectrum of T star. That means if you are able to find point spectrum of T star also, from that we can get the compression spectrum. Okay. Now we know that if T is normal, so let me write as a corollary. If T is normal, then we know that T has a bounded inverse if and only if T is bounded value. So we have observed this earlier. Now when lambda is in a complex number, if lambda is in C, then we can conclude that T minus lambda is also normal. So from the earlier observation we can say that T minus lambda has a bounded inverse if and only if T minus lambda is bounded below. From that we can say that lambda is in the spectrum of T if and only if lambda is in the approximate point spectrum of T. So the conclusion is that if T is normal, then we can conclude that the spectrum of T is exactly approximate point spectrum of T. Okay. and it is easy to check that if T is normal, then the residual spectrum of T is an empty set, because if T is normal, null space of T star and null space of T are same, apply the same result, and we have observed that the relation between the residual spectrum of the operator and point spectrum of the adjoint operator earlier. From that we can directly conclude that the residual spectrum is empty. So hence we can say that in this case spectrum of T is union of point spectrum and the continuous spectrum, and this is again equal to the approximate point spectrum. Okay. Now let us look at properties of self-adjoint, unitary and orthogonal projections, how the spectrum look like. Okay. So if T is self-adjoint, let T be a self-adjoint operator. Then we can say that spectrum of T is subset of R. So this we have observed earlier when we looked at element of a C-star algebra. If it is self-adjoint, we have shown that spectrum is subset of R. Here we give a proof depending on the earlier fact that spectrum for a normal operator is exactly the approximate point spectrum. So let us take lambda to be A plus IB, where A and B are real numbers and B is non-zero. Then we want to show that lambda is in the resolvent set of T. So for x in H, so we can easily look at T minus lambda I at x norm square. We can using inner product, we can conclude this as this is bigger than or equal to B square norm x square for every x in H. This computation can be done using by expanding the inner product. Since B is non-zero, so this implies norm of T minus lambda I x is bigger than mod B times norm x for every x in H. This implies T minus lambda I is bounded below. We know that T minus lambda I is normal, so this operator is normal, so that means it has a bounded inverse, is invertible in B of H. It has a bounded inverse and inverse exists. Inverse is T minus lambda inverse is in B of H. This implies lambda is in the resolvent of T. Okay, so when lambda as non-zero imaginary number, then we have shown that lambda is in the resolvent of T. So that means if lambda is in the spectrum of T, then B must be 0. That means, so this implies spectrum of T is contained in R. Okay. So here we use the fact that when T is self-adjoint, lambda is a complex number, T minus lambda is normal, and use the fact that normal operator is bounded below if and only if it has a bounded inverse. Now let us try to observe the spectrum of a unitary operator. So let me write this as a proposition. Let U be a bounded operator which is unitary. Then we can conclude that spectrum of U is contained in the unit circle set of all Z in C such that mod Z equal to 1. Okay. So we know that for a unitary operator norm is 1, and spectrum of any operator is contained in the closed unit disk with center 0 with radius norm. So we know that clearly spectrum of U is contained in set of all lambda in C such that mod lambda less than or equal to norm of U, that is 1. Now we want to show that if mod lambda is strictly less than 1 as well as mod lambda is strictly bigger than 1, that lambda will be in the resolvent set of U. So let us take lambda in C, then let us try to locate norm of U minus lambda I at x whole square. This is inner product of U minus lambda I at x with itself. So this is nothing but norm Ux square, and the last term will be mod lambda square norm x square, and this is lambda inner product x Ux, and the last term is so lambda, one more term is lambda bar inner product Ux with x. So this we can write as norm of Ux square plus mod lambda square norm x square minus 2 real part of we can write lambda x Ux. Now we can apply the Cauchy square inequality for this one. Real part of a complex number is always less than or equal to modulus of the complex number, and when you multiply with minus, the inequality gets reversed. So this we can say that norm of Ux square, so norm of Ux square is norm x square, so that is nothing but 1 plus mod lambda square multiplied by norm x square minus 2 times mod lambda norm x norm Ux. We are applying the Cauchy square inequality here. So this is nothing but 1 minus mod lambda whole square into norm x square, because norm Ux is here, this is exactly norm x. Okay, so this implies norm of U minus lambda I x is bigger than modulus of 1 minus mod lambda. So when mod lambda is not equal to 1, we can say that U minus lambda is invertible, bounded below. So if mod lambda is not equal to 1, then U minus lambda is invertible. Now U is unitary, it is normal, so U minus lambda is normal. So this implies has a bounded inverse. U minus lambda has a bounded inverse. This implies lambda is in the resolvent. Okay. So from the earlier observation and this observation, we can conclude that spectrum of U is contained in the unit circle. Okay. So for a normal operator, the spectrum is contained in the unit circle, but sometimes it may be possible that spectrum is the full unit circle. So let us see one example. So define the bilateral shift. U of En as En plus 1 for every n in Z, and extend U linearly to all of L2 of Z. This is a bilateral shift. bilateral right shift operator. We know that this is unitary. Now by the earlier observation, by the earlier result, spectrum of U is contained in the unit circle. Okay. Now let us take lambda is in the unit circle. We want to show that lambda is in the spectrum of U. So define xn as square root of 1 by square root of 2n plus 1 summation k equal to minus n to n k by lambda power k. So here En is a standard orthogonal basis for L to Z. So the standard ONB for L2 of Z. Okay, now if you look at U minus lambda I at xn, now square, if you look at L2 now, so this is nothing but 1 by root 2n plus 1, and here if you look at U of so this is norm of summation k equal to minus n to n e k plus 1 by lambda k minus lambda xn. This is e k divided by lambda k minus 1. This is L2 now. So if you compute this one, you will get 1 by square root of 2n plus 1. So this is a telescopic sum. You will get this is En plus 1 by lambda n minus E of minus n by lambda power minus n minus 1. This is L2 now. We know that L2 norm of En is 1 for every n, but the difference is square root 2. So this is, and we also know that mod lambda equal to 1. So this is square root of 2 divided by 2n plus 1, and we know that this goes to 0 as n tends to infinity. Okay. So this implies that lambda is in the approximate point spectrum of U, but since U is unitary, that is exactly equal to the spectrum of U. So we have shown that if lambda is in the unit circle, then lambda is in the spectrum of U. So therefore we can say that spectrum of U is exactly the unit circle. Okay. So far we have discussed about spectrum of normal operators, spectrum of self-adjoint operators, spectrum of unitary operators, and now let us look at spectrum of orthogonal projection. So let P be an orthogonal projection. Then spectrum of P is contained in the set consisting of two elements 0 and 1. Now we know that as P equal to P star, that equal to P square, so we can conclude that spectrum of P is subset of R. Now using the spectral mapping theorem, so lambda in the spectrum of P implies lambda square in the spectrum of P square, that is spectrum of P. So from this we can say that since p square equal to p, you can conclude that I am repeating again. So since spectrum of p square repeating again, as since p square minus p equal to 0, we get that by the spectral mapping theorem. So lambda square minus lambda is 0 for all lambda in the spectrum of p, or we can say that lambda square equal to lambda. So that is lambda is 0 or 1. Spectrum of p is contained in 0 or 1. So another way to prove this is that you take lambda outside. So alternatively, if lambda is not inside this set, then show that p minus lambda I at x is k times norm x for every x in h. There exists some k. That means we want to show that it is bounded below. I am repeating again. So alternatively, so as p equal to p star, we have spectrum of p is subset of R. Now choose lambda. So let us take lambda in R minus 0, 1. Then we can look at for x in h, p minus lambda I at x, norm of this. This can be written as norm of px minus x can be written as x plus I minus px. So this is nothing but 1 minus lambda px. This is p plus I minus px. So if you take square everywhere, you will get, now these two vectors px and I minus px, they are mutually orthogonal. So we can say that when you take the square here, we will get 1 minus norm at px square plus here we get lambda mod lambda square I minus px. So this is nothing but, this is bigger than, take minimum of 1 minus mod lambda square mod lambda square. So this is norm px square plus norm I minus px square, and this is nothing but minimum of 1 minus mod lambda square norm x square. So this is positive because lambda is not equal to 0, lambda not equal to 1. So we can conclude that p minus lambda is bounded below. Since p minus lambda is a normal operator, we can say that it is invertible. So whenever lambda is outside 0, 1, p minus lambda is invertible. Hence we can say that lambda cannot be in the spectrum. So from this we can conclude the result. Okay, so this is about spectrum of a orthogonal projection Now if T is a positive operator, then we can conclude that spectrum of T is subset of the positive real line. So proposition, let T be a bounded operator which is positive, then we can say that spectrum of T is contained in the closed interval 0, non-T. So since T is positive, T is positive implies T is self-adjoint, and this implies spectrum of T is contained in R. Now the idea is that if let us take lambda in R with lambda strictly less than 0, then consider T minus lambda I. So I will give a hint here. So we can follow the same method which we used earlier. So show that T minus lambda is bounded below. Now T minus lambda is a normal operator. So from that we can conclude that T minus lambda I has a bounded inverse. That means lambda cannot be inside the spectrum of T. So from this we can conclude that spectrum of positive operator is positive subset of the real line. Now from these results, for example, we have seen spectrum of unitary operator is subset of the unit circle, spectrum of self-adjoint operator is subset of the real line, spectrum of projection is subset of the set 0, 1, and spectrum of positive operator is subset of positive real line. So looking at these spectrums, we can actually compare normal operator with complex numbers, because we know that when T is normal, T can be written as A plus IB, the Cartesian decomposition, such that A and B are commuting. So if Z is a complex number, Z can be written as X plus IY, where X and Y are real numbers which commute. And when T is self-adjoint, we can compare self-adjoint operators with real numbers, because spectrum of T is subset of R, and spectrum of unitary operator is subset of circle. So unitary operator represents the circle, and spectrum of positive operator is subset of R. So positive real line is compared with positive operators. Okay, so in the next class we discuss some more important properties about the approximate point spectrum and some more other important properties of the spectrum. I'll stop here. Thank you very much.